Hello and welcome to another exciting episode on our channel. Today, we are diving deep into the world of electrical engineering and motor technology as we embark on an intriguing project featuring a dedicated three-phase squirrel cage induction motor by Festo from the Labvolt series. This hands-on experience will allow us to explore the intricacies of motor assembly, operation, and performance testing. To assemble it, we will need the following materials supplied by Festo: a support module, front and rear flanges, a stator, a rotor, a pulley, winged screws, a faceplate and a rubber hammer. As we progress through the video, you'll see me putting these essential components together one by one, preparing for the assembly process. To begin assembly, I will carefully install the front flange onto the front squirrel rotor bearing, using the rubber hammer to ensure a smooth and secure fit without damaging any components. Once the front flange is in place, I will position the rotor inside the stator and secure it with winged screws, preparing the motor for the next steps. Next I will install the rear flange to the rear of the motor case, again using the rubber hammer for precision and care. After installing the rear flange, I will attach the pulley to the rotor. Next, I will mount the motor onto the bracket module and secure it using the additional screws that came with the bracket. To complete the electrical connections, I will connect the stator wires to the support wires. Finally, I will attach the faceplate to the front of the support module, completing our meticulous assembly process. Now I'll start by removing the existing module from the workstation, ensuring a clean and organized space for our next process. Additionally, I will disconnect and remove the connecting belt to clear the area and make space for the new motor setup. Now, after removing the existing module from the workstation, we are ready to install our freshly assembled motor module. Carefully aligning it with precision, I will secure it in place and connect it to the dynamometer using the pulley belt. It is crucial to be very careful during this step, especially when removing the belt, as improper handling could potentially cause injury or damage to the fingers. Now, it's time to put our assembled asynchronous squirrel cage motor to the test. I will connect its phases to the 3-phase power supply using banana plugs in a star coupling configuration. Ensuring all connections are secure and correctly aligned, I will then start the motor to verify its functionality and performance. Now let's start collecting data and monitoring the performance of our engine in real time. I will connect the computer to the data acquisition unit using a USB connection, and then connect this unit to a 24V power supply. Additionally, I will connect the computer to the drive motor, also known as the dynamometer, using another USB connection. Now let's move on to the data acquisition and control process by opening the LVdac software on our computer. This software will allow us to monitor and control the dynamometer with precision. I'll start by selecting the appropriate connection mode and configuring the power grid voltage and frequency to align with our configuration. Following this, I will configure the necessary parameters that need to be read and collected during the testing phase. Now, let's take a closer look at the schematic of our circuit to better understand the connections and components involved in our setup. Our circuit is connected to a 3-phase power supply, which serves as the primary energy source for our system. The power supply is linked to the data acquisition module, which features voltmeters E1 and E2 to measure voltage levels and ammeters I1 and I2 to measure current levels. Additionally, the power supply is connected to the 3-phase induction motor, which is coupled in a star configuration to ensure proper operation and efficiency. This schematic provides a clear overview of the interconnected components and their roles within our system. Now that I have configured the LVdac software, we are ready to conduct a speed sweep test on the drive motor. The motor will run through a range of speeds, starting from an initial speed of 1,500 RPM, which is the synchronous speed of the 4-pole cage motor. It's worth noting that the rated speed of this motor is 1,360 RPM at 50 Hz and 380 volt. The speed will gradually decrease to a final speed of 200 RPM. The test is divided into 10 speed steps, with each step lasting for 7 seconds. During each 7-second interval, the LVdac software will gather data on various parameters. After completing the test, I will extract the collected data from the LVdac software and paste it into an Excel spreadsheet for further analysis and visualization. Now let's move on to the second speed sweep test, this time with a different set of settings. The initial speed for this test will be 40 RPM, and we will have a total of 16 speed steps. The test will end with the motor stopping completely, reaching a final speed of 0 RPM. After gathering the data from both the first and second speed sweep tests and pasting it into Excel, we are now ready to visualize and analyze the results. I will plot the charts of torque for the three-phase induction motor as a function of the sweep speed of the drive motor. In the first test, starting with an initial speed of 1500 RPM, which is the synchronous speed, as the drive motor's speed decreases, the speed of the three-phase induction motor also decreases. However, it's important to note that even though both motors rotate in the same direction, the decrease in speed of the drive motor affects the speed of the induction motor differently. In this test, the final recorded speed is 968 RPM, not the intended 200 RPM. The torque of the three-phase induction motor varies across the speed range. The torque values increase from -0.10 at 1500 RPM to 3.7 at 968 RPM. This increase in torque can be attributed to the motor operating at a reduced speed relative to its synchronous speed. As the motor's speed decreases, the slip difference between synchronous and operating speed increases, leading to an increase in torque. This phenomenon is consistent with the characteristics of squirrel cage induction motors, where higher slip results in higher torque. In the second test, starting with an initial speed of 40 rpm for the drive motor and 1360 rpm for the induction motor, as the drive motor's speed decreases, the speed of the three-phase induction motor also decreases. Both motors rotate in the same direction, and the decrease in speed of the drive motor affects the speed of the induction motor differently. In this test, the final recorded speed is 844 rpm, not reaching the intended 0 rpm. The torque of the three-phase induction motor remains relatively stable across the speed range. The torque values fluctuate slightly, ranging from 3.77 to 3.73. This minimal change in torque can be attributed to the motor operating at a reduced speed relative to its synchronous speed. Despite the speed reduction, the torque remains relatively constant, indicating the motor's ability to maintain consistent performance across a range of speeds. In this comprehensive study, we performed two speed sweep tests on a three-phase induction motor to analyze its performance under different operating conditions. Testing involved connecting the motor to a drive motor via a dynamometer and monitoring various parameters using LVdac software for data acquisition. The phenomena observed during these tests can be explained by the operating principles of induction motors. When an induction motor operates at a speed lower than its synchronous speed, a phenomenon called slip occurs. This slip results in a difference between the speed of the magnetic field, synchronous speed, and the speed of the rotor, leading to the production of torque. The higher the slip, the higher the torque produced by the motor. In the first test, the increase in torque with decreasing speed is a direct result of increased slip as the motor operates further from its synchronous speed. On the other hand, the second test demonstrated the motor's ability to maintain constant torque despite the speed variation, highlighting its stability and reliability. Thanks for watching and see you soon in the next videos with other types of electrical motors.